Okay, good afternoon. Thanks for showing up in this turkey-encumbered week. We've been talking about sugars and some of their reactivity. And as polyhydroxyaldehydes, they do everything that you expect them to do, but they have superimposed on them the twist of multifunctionality, so you have to worry about selectivity, and the fact that sugars are in equilibrium acyclic with cyclic forms of hemiacetals, and that they have this unique carbon, which is the hemiacetal carbon, which is much more reactive than all the other hydroxy-bearing carbons. And so therefore we learned about selective oxidations, 3 of them, one of them non-selective, but oxidations. The first one was bromine in water that oxidized the aldehyde function on top selectively to the so-called aldonic acid, so you get the monocarboxylic acid. The second one was selective terminal double oxidation, the aldehyde function as well as the hydroxymethyl at the other end, at the bottom, in the Fischer projection, with nitric acid, and that gave the so-called aldaric acid. So these are dicarboxylic acids, which may or may not show symmetry. And then we did the destructive oxidation, where every single carbon-carbon bond is broken. That was per iodic acid. And that cleaved every single bond. If you look down the Fischer projection, that's the easiest way to look at it. Every vertical CC bond's broken. And one way to think about it is that you cap off the carbon radicals that you get by cleaving that bond with OH functions, and you get the oxidation state of the product. And we found that this may be useful to identify how many carbons there are in the molecule. Is it a hexose, a pentose, a heterose, and whether it's an aldose or ketose. Is it an aldehyde-derived sugar or a ketone-derived sugar? And then we did reduction, sodium borohydride. That was absolutely nothing new there, except that it works because, again, the cyclic hemiacetal form, which is there dominantly, is in equilibrium with the aldehyde form, and that gets reduced. And then we did esterification and etherification, and typically there often, if you want to protect the whole sugar, you just do global reactions, so everything is esterified or everything turns into an ether. But if you want to selectively just protect the hemiacetal carbon, you can do this with mild acid and an alcohol. Okay? That makes the carbocation selectively at that carbon. And if you look at the model, that's the hemiacetal carbon right here, the one that has the 2 oxygens on it, the cyclic, the oxygen in the ring, and the OH here. That's the labile carbon, and you can readily protonate here, make water leave, and that carbocation, stabilized by this oxygen, then accepts an alcohol, and that blocks that site as the full acetal. It's classical acetal formation, except that it's a cyclic system. And conversely, if you have fully protected all around, you can selectively hydrolyze a protected OH here. If this is an acetate or a methoxy, and these are all either esters or ethers, you can selectively cleave here and liberate the acetal carbon, meaning you liberate the aldehyde function, okay, when everything else is protected. And that is sometimes useful if you want to do selective transformations. And so we left it off here at that stage, and today we're going to finish off a couple of processes that deal with sugar synthesis, in particular the buildup of longer sugars from shorter sugars by 1 carbon chain extension, and the reverse of it, namely the shortening of a sugar by 1 carbon chain reduction. And so the first one is called the Kiliani-Fischer extension, named after these two chemists, Hani Kiliani and Emil Fischer. This Fischer actually is considered the father of all sugar chemistry. He single-handedly actually elucidated the structures of all of the aldohexoses, all the 8 aldohexoses that you saw tabulated in a table, by using the tricks that we have started to get an inkling of symmetrization with specific reactions and similar things. Remember, in those days, there was no spectroscopy, and so he had to rely entirely on chemical correlations. And for this, he got the Nobel Prize in 1902. So and part of his strategy actually was this extension, as well as the next one, the chain degradation. So how do we extend the sugar by 1 carbon? So the idea is to start with a sugar, generically written like this, with a wiggly line here. It could be the smallest sugar, dihydroxypentanal or glyceraldehyde, where this would be a hydrogen down here, so this would be CH2OH, or anything longer. Okay? And the trick is to use the reactivity of the aldehyde function and add HCN. That's a reaction we know of. It's a standard HCN addition to the CO double bond, and that makes the alpha hydroxy cyanide. And again, to drive home the point, it's really easy if you use Fischer stencils to just add another stereocenter. You just add another cross on top of these guys here. So you make this carbon a cross, and on top you put the nitrile. And when you do this, notice, of course, that this carbon, once you add HCN, becomes a new stereocenter, okay, because there are 4 different substituents. And so in the Fischer projection, the way to show this is to show OH is either to the right or to the left. It's totally simple. We don't have to worry about RNS unless you're specifically asked to specify, is this ROS? We're really more concerned about relative stereochemistry. So you get 2 compounds, actually. And that's, if you wish, a drawback of this method, but you can also say, you can put a positive spin on it and say, well, you get 2 new sugars from 1. Okay? And so at this stage, the task remains of turning this nitrile into an aldehyde, and that will give you the new sugar. And the way to do this is to reduce the nitrile function by catalytic hydrogenation. Now, we've done catalytic hydrogenation of nitriles as a source of primary amines, and that was fully hydrogenating the 2 double bonds of the triple bond. What we're using here is a trick, namely use a poison catalyst, that you may recall Lindlar catalyst from chapter 13. We use poison catalyst in chapter 13 to stop the hydrogenation of an acetylene at the dihydrogenation stage. That is, 1 mole of H2 has been added. That was a way to make cis alkenes. Okay? So, and you do this by poisoning the surface of the palladium catalyst. These catalysts are heterogeneous, so they're black powders, and they have active sites on the surface. This has all been investigated and scrutinized and defined. And when you add a poison, and this can be a variety of substances, in the Lindlar type catalyst, you add barium sulfate, then the activity of the catalyst is reduced. It will only hydrogenate the first pi bond of a triple bond, which is the more reactive pi bond. So it turns a triple bond into a double bond. So you could, if you remember palladium with barium sulfate, that's great. You can also just write poison palladium catalyst. Okay? Or if you remember Lindlar, use the term Lindlar. That's perfectly fine, as long as you express the fact that this is a specially deactivated catalyst. And when this happens, notice what happens to the nitrile. It turns it into an imine. And you're running this under slightly acidic water conditions, and typically you put a little pressure of hydrogen, and under these conditions, of course, an imine like that won't survive. It will hydrolyze instantly. By the usual hydrolysis of an imine, protonation of nitrogen, then water attacks the carbon, and eventually, ammonium is being kicked out, and this turns into the corresponding aldehyde, and there you are. So it's a two-step procedure, HCN addition, followed by dehydrogenation. And typically, actually it depends, you can separate the two diastereomers either at this stage or at the final stage where you get the two different sugars if you want to isolate the two different sugars and do whatever you need to do with them. And, of course, if you now want to extend it by one more carbon, you can keep on going. Okay? And this methodology, of course, is applicable to other systems which are not sugars, okay? Because this is quite general. It doesn't depend on the fact that you have a polyhydroxy tail hanging off at the bottom. Okay? So here's an example. If you start with this pentose, so 5-carbon aldose, which with this stereochemistry, or these two OHs to the left, this one to the right, is called lysose, and apply the Kiliani-Fischer extension, HCN addition. Typically, actually, you don't use HCN gas, although you can. It's safer to use potassium cyanide and acid, which is a source of HCN. And then use the poison catalyst hydrogenation. You get two new sugars where the HCN addition adds a carbon, which is this carbon, in which you have 50-50 chance, roughly, of having OH on the left or having OH on the right. It's not exactly 50-50 because this is a diastereomerization, so the transition states leading to the two are slightly different in energy. But in practice, you get an almost equimolar mixture for most sugars. And so OH is to the left, OH is to the right. And so these are now hexoses as opposed to pentoses, and the one with the OH to the left is called hallose, the one to the right is called galactose. Galactose, you probably have heard of as a sugar. It's just recently got some press because yet another old wives' tale prejudice of people debunked, namely that drinking a lot of milk is good for you. You probably all grew up with that. I certainly grew up with that, although I never quite believed in that. Particularly when you live in Bavaria, drinking beer is considered good for you, not drinking milk. And it turns out that the idea that drinking milk is good for you was because of vitamin D. Vitamin D strengthens your bones, and so the idea was that you would prevent bones breaking, in particular at older age. And the problem is it actually does exactly the opposite because the lactose in the milk is metabolized to galactose. And galactose causes oxidative stress on your system and actually makes your bones more brittle in the end. And so a big study involving 100,000 people followed over years and years shows that, indeed, too much milk may be detrimental. So the 3 glasses of milk per day has been now debunked. So that's galactose, anyway. So the opposite strategy is to reduce the carbon chain. And that's called the Ruff degradation, after the German Otto Ruff. That's how you pronounce this. And he found that you can decarboxylate the aldehyde carbon after you've turned it into the carboxylic acid. So what he found is that when you oxidize the aldehyde carbon of a sugar, and he uses bromine and water, the technique that we've learned before, so that's no new vocabulary. You make the aldonic acid, so this is COOH, and then he applied a one-electron oxidizing system, which involves iron 3+ as an oxidizing agent. So iron 3, like many of the transition metals in the higher oxidation states, they're oxidizing agents. We've used manganese, we've used chromium, we've used a bunch of other systems. So iron 3 is part of that, and iron 3 is iron in the rust state, if you wish, and it gets reduced to iron 2. And so iron 3 is the catalyst that enables electrons to jump back and forth in and out of the iron, and it turns to iron 2. The stoichiometric oxidant is actually hydrogen peroxide. Now, you could have used stoichiometric iron 3. That's perfectly reasonable. You just use one equivalent or two equivalents of iron 3. You actually need 2, as we'll see in a second. But iron is expensive. Hydrogen peroxide is way cheaper. Relatively expensive. So hydrogen peroxide is way cheaper, and it's more easily run, this reaction. You don't have to separate out the iron 2 salt from your reaction mixture. So iron 3 is used in catalytic amounts, and when it gets reduced to iron 2, the hydrogen peroxide that's there in one equivalent reoxidizes the iron 2 back to iron 3. And the hydrogen peroxide doesn't do that decarboxylation chemistry. So with this melange, and you actually do this on a slightly basic condition, so I've added one ingredient which adds it's buffered, really. It's carbonate. So this is calcium carbonate. You can use any carbonate to facilitate this. CO2 blows out. Okay, so this is by a different mechanism than the decarboxylation of a 3-oxocarboxylic acid that we learned about last week. And you're losing this carbon, and this carbon turns into the aldehyde carbon. And notice that when you do that, the stereochemistry at this carbon, of course, disappears. So in fact, regardless of whether the OH here is to the right or the OH is to the left, you get the same lower aldehyde, logically. Okay? So this is a reaction where when you reduce the chain length, 2 sugars will give the same aldehyde, as opposed to the Kiliani-Fischer extension, where 1 sugar gives 2 new aldehyde sugars. Okay? So what's the mechanism of this? I'll show it to you briefly. I won't test for this. But this goes through the carboxylic acid, turning into the carboxylate, so the slide base, the carbonate, protonates, so loss of proton, and so you get CO2 minus. You get the carboxylate. And that carboxylate is oxidized by the iron 3. To put this differently, the iron 3 rips out an electron from the carboxylate and turns into iron 2. Okay? So what is left is a carboxy radical. Okay? Remember, you started with 2 electrons here. So this was 3 lone pairs around this oxygen, making it negatively charged, a typical carboxylate anion. When you take an electron out of that, the negative charge disappears, of course, and you now have a radical. And at this stage, this CO2 unit realizes it can liberate itself, stabilize itself, by just leaving, by cleaving this bond here, heterolytically, taking 1 electron with it, and that makes carbon dioxide. That single electron that you get by uncoupling the electron pair of this bond couples with this electron, and that makes the second CO double bond. CO2 blows out. What's left behind is a new radical, which is a hydroxy radical, which is highly subject to a second oxidation step. So the overall process is a 2-electron oxidation. So when you oxidize this, you basically take the electron out of this carbon, and another iron 3 turns into iron 2. And when you do that, this puts a plus charge on that carbon. In other words, that second electron jump makes a hydroxycarbocation. And by now, the bells should ring in your brain. Hydroxycarbocation is nothing else but protonated carbonyl. So that finishes it. All you need to do is deprotonate the carbonyl, and you get the aldehyde function. And the iron 2 that's generated is then reoxidized with the hydrogen peroxide that's floating around. That is the stoichiometric oxidant, and that's why you use only a pinch of iron 3 to enable that relay reaction. Okay, so here's an example. We can start either with this aldohexose, happens to be called talose. These 3 OHs on the left. This one, of course, is on the right because I'm always picking the D sugars, only one enantiomer of both. And so in the D sugars, remember that last stereocenter down here, OH is always on the right. But the other guys are all on the left. And you can start, for example, with this one also, and that's again galactose, where only these 2 OHs are still on the left, but this one now is on the right. In other words, if you look at the top stereocenter, the OH up here is to the right, it here is to the left. And I'm pointing this out because both of these, when you subject them to the rough degradation, that is oxidation to the carboxylic acid, followed by decarboxylation, loss of CO2, and this carbon turning into this aldehyde, the stereochemistry at this carbon is lost. So both of these compounds give the same lower sugar. Okay? And you can see how one can use this in order to deduce structures of unknowns by correlating them by either the extension of the chain or the reduction of the chain, ultimately with a known sugar. So it gives you some knowledge about the stereochemistry around the stereocenters down the chain. So at the end of this chapter, yes, sorry. It's arbitrary because most of them are the naturally occurring sugars. And so we're sticking with, I could have done the racemic mixtures, okay, which we've done up until now. Whenever, in most cases, when we had a chiral compound, we only showed one enantiomer when we showed stereochemistry, but it was tacitly accepted that what I meant was the racemate, 50-50 mix of both enantiomers. Here we're just sticking with one enantiomer, in part because there's so many stereocenters that, and we are looking specifically at relative stereochemistry with the Fischer projections that are shown like this. It's just easier to just stick with one enantiomeric series. So they're all optically active, only image, and it's defined by this guy always being on the right. Okay? So every single compound in this chapter that we talked about has an enantiomer, has a mirror image, okay? And the arguments are the same. So at the end of the chapter, we have a collection of the applications of sugars in biology and in medicinal chemistry. There are many, many sugar derivatives that occur in nature, and perhaps the best known is sucrose, okay? Also known as table sugar. Okay? Sucrose is a beautiful crystalline compound. I don't know whether you've ever really consciously realized that there are very few pure compounds that we ingest. If you eat a hamburger, that's a mixture of millions of compounds. Okay? Soup, a steak, what have you. It's not a pure compound, but sucrose is, and that's why it's actually a crystal. The other example is sodium chloride, table salt. That's a pure salt, crystalline, and so on, and you can recrystallize it. Okay? So here's a picture of the crystals of table sugar. Now, one of the stunning things about table sugar, of course, it tastes sweet, and this is something that's been very attractive to us, presumably for evolutionary reasons. We were drawn to sweet fruits and sweet vegetables because they contain sugar, which is high calorie, is fuel. And so we're drawn to the fuel, that's survival. Okay? But of course, there's pleasure associated with that too. And we're now consuming about 150 pounds per person per year worldwide of sugar. Okay, so this is a combination of the sugar we buy and stick in our coffee and tea in the crystalline form, a lot of it in our food, adulterated food, sweetened food, sodas, and ice cream, and cakes, and all that stuff. But almost everything we eat, vegetables and meat products, they contain sucrose. So 150 pounds per person per year. Now, the statistics on this go back to around 1820. In 1820, the worldwide consumption per person was 7 pounds. Okay? So you can see what has happened to us. We are eating 20 times as much sugar than we did before, and now there are emergency calls by epidemiologists and doctors that say that sugar actually in these quantities is actually dangerous to our overall health, and that's part of the push to reduce our sugar intake. Actually, this curve that I just saw last night goes up steadily over the years, but in the last 3 years, it's going down. Okay? Now, I don't know that this is just a temporary blip and it's going to go back up, but that's a good sign. Yes?
So, what's the difference between, consumption of table sugar with, high fructose corn syrup? Is it just fructose in that case?
Okay, so I'm coming to that, actually. That's a good question. The question was, what's the difference between this and high fructose corn syrup? And the short answer is none whatsoever. Because the structure of sucrose is exactly 1 mole of glucose and 1 mole of fructose. And high fructose corn syrup is making the same mixture because it tastes good, 1-to-1, by fermentation and other processes from plant sources. And the name, so there's a little blurb in your text, the name high fructose is a complete misnomer. It doesn't mean that there's unusually high fructose levels in this. It just means that it has to be brought up to 50% in the mixture with glucose in order to absolutely mimic sucrose. And so, and there's absolutely nothing bad about it. It's the same, unless, now people say too much sucrose is bad for you. So sugar itself in large quantities apparently is associated with the high incidence of diabetes. That's the theory. There seems to be fairly good studies now that correlate this, and heart disease and other